Okay, so we have seen the excess force between the faces AC and BDS, dm by I integral y to y1 b into dy into y. So please take care. I have taken from this level to this level, right? From this level to this level is y. From here to the top fiber is y1. Okay. So excess force between the faces AC and BD we have taken. Now I am coming to say that integral y to y1 b into y into dy. What is that? What is b into y? B into y is the area of that element. Sorry, b into dy is the area of the element. So b into dy is the area of the element. That is b into dy is area of the element. The area into y. What is y? Y is the distance of the element from the neutral axis. So y is the distance of the element from the neutral axis. So you are taking moment of this particular element. You are taking moment of this particular elemental area about the neutral axis, right? So you b into dy into y is the moment of the area of the element about neutral axis, right? So you are taking moment of the area of the element about neutral axis, or you can just rewrite this as integral y to y1 b into y into dy is, you can take the whole area into y, or you can say it as a y bar, no problem, because y bar actually is the what do you call, actually if you take an elemental distance and if you take moment of this particular area, actually it is a centroidal distance from the neutral axis, understand? So you normally use y bar as a distance of the center of gravity from a particular reference. Okay, so I am just rewriting this as b into dy is the area, y I have taken as y bar if you are taking the total area, understand? So this excess force which we have found out is balanced by a shearing stress toe acting along PQ, right? So this is the plan of the particular cross section. That means if you look from this top, if you look from this top of this particular element, you will have the width as dx and depth as b, understand? That means if you are just looking like this from the top of this, right? If you look from this on the beam, this is dx and the depth is b. So that is this particular portion I have drawn here. So you will have, this is dx and this is b, and the bending stress on this face is m by I into y, and the bending stress on this face is m plus dm by I into y. So in order to resist this excess bending stress force due to the excess bending stress, you will have the shear stress being developed to resist that. So this is toe, and this toe is acting on which face? This toe is acting on this area, that is dx into b, understand? So I will just explain once again. We have taken the excess forces integral y to y1 into b into dy into y, dm by I have taken outside. So we have specified what is this integral part. Integral part is this, b into dy is the area, y is the distance of the element from the neutral axis. Since it is a very small element, distance to the element itself is the distance of center of gravity to that particular element. So I have rewritten as this integral part I have taken as the total area and the distance as y bar. So you get this as a into y bar. So this excess force which we have found out as, it has to be balanced by the force due to the shear stress developed. So I have taken the top view of this particular portion. Top view I have just looked up from this particular level. You can just look at this particular figure. So in that particular figure you can see that this is the width dx and the width of that particular element at that particular section is b. So and on this side you have the bending stress as m by I into y, and at this level we have got m plus dm by I into y. So there is an excess force developed due to the change in bending stress. So that has to be resisted by the shear stress developed, and the shear stress is developed on this hatched area, and that hatched area is what? dx into b, right? So this is the level PQ we are talking about, right? So we have got the bending stress force we have got and the shear stress force. Now what is left? We have to equate these two. So the next step will be you equate the force due to shear stress is tau into B into dx, and the other one was dm by I into A into y bar, that is equal to tau into B into dx. So we get from this tau is equal to dm into A into y bar divided by IB dx. But you already know that dm by dx is equal to shear force. So you apply that. So that's what I was telling. Whatever we have learned in the previous classes, that has to be used in each and every step of our learning procedure. So you cannot forget anything. So please keep doing refreshing all those formulas and derivations we have done. So dm by dx becomes shear force. So we are rewriting dm by dx as F. You will have F A y bar by IB. So this is the fundamental equation for solving shear stress at any section. Understand? So I have described all the terms where B is the width of the beam at the point where shear force is considered. That is very important. You cannot just take the width of the beam as B, because if it is a nominal cross section of B and D, it is okay. Otherwise you cannot do that, because if it is a T section or if it is an I section or if it is a triangular section, the width is varying at each and every point. So you have to take the appropriate width at the section under consideration. So B is the width of the beam at the point where shear force is considered, and AY bar, that is also another important definition. AY bar is the moment of the cross-sectional area above the point under consideration about neutral axis, right? AY bar, you can just read once again. AY bar is the moment of the cross-sectional area above the point about neutral axis. Okay, so you have to take up the whole area above that. That is why the integral y to y1 which I have specified, because under the level, what is the level of y? Above that, y to y1 we have to take. What is the level under consideration? Beyond that level, you have to take the whole area and take the moment of that particular area about neutral axis. So what you can infer from this is that it can be noted that the shear stress at the extreme fiber will be 0 as per the equation. How can you say that? Because we have said that AY bar is the moment of the area of the about neutral axis, about the level under consideration. So if you talk about the extreme fiber, there is no area above that. Understand? So the area above that is 0. So naturally at the extreme fibers, the moment shear stress will be 0. So this you have to understand very clearly. So your fundamental equation for shear stress is FAY bar by I. Okay. So if you just go through the typical case of a rectangular section, which is the simplest one, we can just see here. This is the you have started the case 1. Your equation is FAY bar by IB. So if you take a cross section over here, you can taking the breadth as B and depth as D. You already know the neutral axis, which is going at D by 2. So I have taken a neutral axis over here. So I have taken a layer instead of PQ in that particular derivation. I have taken a point layer PQ over here at a distance y from neutral axis, right? So your area under consideration is the hashed area, that is the area above the level under consideration. So we have marked everything in the figure. So this is Pakka complete. Okay. Now you come to your formula. So your formula is tau is equal to FAY bar by IB. Okay. So your problem is to find out AY bar. That is the first step, right? All others are okay. So what is the area under consideration? Area under consideration is this shaded area. Okay. What is this shaded area? Width is B. What is the depth? What is the depth? Depth is nothing but from here till here is D by 2. Am I right? This particular value is D by 2 minus Y. So you get this particular equation as D by 2 minus Y is the depth, width is B. So you will have the equation as B into D by 2 minus Y. So it is a rectangular portion. width is b and this height is d by 2 minus y. Now what is the center of gravity of that particular area from neutral axis? So its center of gravity is at the center of this, because this is a rectangular area. So you know that the center of gravity of this shaded area will locate it at the center of this. So what is y bar from neutral axis to the center of the shaded area, or to the center of gravity of this shaded area? So what is this y bar coming to? From here till here is y. What is this depth which we have already studied? That is d by 2 minus y. So the center of this will be d by 2 minus y by 2. So that is what is being written here. D by 2 minus y by 2 is the midpoint of this. But you have to take moment about the neutral axis. So I have taken y plus. So I have taken y plus d by 2 minus y by 2. Then only you get the distance from the neutral axis. So you are taking the distance as from neutral axis to the center of this shaded area. This is your y bar value. Understand? So this y bar value is now y plus half of this is d by 2 minus y by 2. So taking the LCM, you will get this particular equation. So please substitute in this particular equation. F, you can keep it as such. A y bar, now you have got what is capital I? Capital I is moment of inertia, the whole cross section. So what is capital I for rectangular section? This b dq by 12. Then what is b? B is the width under consideration. So at this particular level, width under consideration is b itself. So as per the formula also it is b. So as per your figure also it is b. So you can just substitute all the values and you can just find out what is the final answer. Please try.